Maybe the simplest real-world NLP application is text classification. This takes many forms. For example, classifying email as spam, labeling a review as having positive or negative sentiment, identifying the topic of an article, etc. The way the task is defined is we're given an input text and must label it with a category from some fixed set. The standard approach for solving these tasks is to use data. So where does this data come from? Well, NLP datasets have inputs, usually some form of text, and outputs, often some sort of annotation, like a category in this context, but we'll see other types of annotation as well as other output types later in the course. When doing supervised machine learning, we assume labeled datasets, and we refer to labels as ground truth. In NLP, labels are provided by humans, and there's always some amount of disagreement. We typically refer to the annotations or labels as the gold standard rather than ground truth. There are many ways of collecting annotations, which we'll talk about briefly. The first is to use paid, trained human annotators. This is the traditional approach and involves researchers writing extensive annotation guidelines to attempt to handle all the subtleties of a task. The annotators often have linguistic expertise and are trained to do the task. This leads to high-quality, consistent annotations, but is costly. The most famous example in NLP is the Penn Tree Bank, developed in the early 90s. It has 1 million tokens of newswire text, annotated with part-of-speech and syntactic parse trees. The second method is crowdsourcing, which started to become popular around 2008 or so. You can't really train annotators here, but you can easily reach a large number of non-expert annotators, so it's feasible to get multiple annotations, and then average or combine them. This can produce data that's roughly as good as that from trained experts. One example is the Stanford Sentiment Tree Bank, which is a sentiment classification dataset with labels on constituents in a sentence. Annotators were shown a phrase and a sentiment slider, and multiple annotations were obtained for each such phrase. The third category is to find annotations that appear naturally, say on the web. This sort of data was key to the statistical NLP revolution, exemplified by work happening at IBM in the late 80s. This is a slide that shows how IBM researchers were viewing data. The phrase, "there's no data like more data," captured how they kept finding better results by adding more and more data, even if the domain of the text that was available didn't always match what they were looking for. And today, this type of data is as important as it ever has been, due to the vast and growing amounts of text in electronic form. Okay, we'll assume we have data for text classification that takes the form of XY pairs. X is a textual input and Y is a classification label. We write the input X in boldface to indicate that it's a structured object, unlike the classification label Y, which is not structured and can be thought of as a scalar. We'll make a distinction in our notation between a vector and a structured object like a textual input, using italics for the latter. Then what is a classifier? Well, we'll think of it as a function from inputs X to classification labels Y, and we'll focus on one simple type of classifier. The key ingredient is a score function that for any input X and candidate label Y returns a scalar score computed using parameters W. Then the classifier is captured by this classify function that simply returns the argmax of the scoring function over all possible labels. Given our classifier definition, there are 3 problems we need to address to build and deploy a classifier. First is modeling. How do we assign a score to an XY pair using parameters W? Second is inference. How do we efficiently solve this argmax? That is, search over the set of possible labels. For text classification, this will be easy, but for other tasks, inference can be much more challenging. Finally, learning. Given a score function parameterized by W, how do we use data to choose the values for W? We'll be using the same formulation throughout the course, even when the output space is exponentially large or even unbounded, as in tasks like machine translation. So we'll be returning to this many times in the future. In the next few videos, we'll talk about modeling and learning for text classification. So first, we need to talk about experimental practice. The first innovation in working with data-driven methods is to split the data. Some portion you use to fit the model or estimate parameters, called train, and a separate portion you use to evaluate your model, called test. The motivation is to simulate the conditions of applying this model on new data that you would encounter in the real world, rather than primarily focusing on how well you can fit the data that you already have. But there's a problem here, right? We typically want to try out many ideas, which involves evaluating on the test data many times, but then that test data is no longer a simulation of real-world conditions. So how should we explore and evaluate choices in building systems? People sometimes use cross-validation on the training set, but that's not practical for large training sets. So the second innovation is to divide the data into not just train and test, but also a third set called development or validation, which we use to evaluate in preliminary experiments. Then once we're finished the research project, ready to submit the paper, we evaluate our best model on the test set. However, there's still a potential problem with this. If we have a lot of things to tune, we can end up overfitting on the development set. It's no longer a good predictor of how our model will perform on the test set because we've used it for too many decisions. So a better idea is to have another split. In addition to train, dev, and test, we want another test set we can use for preliminary testing, sometimes called dev test. It's also good to have multiple test sets so that when one begins to get contaminated from too much testing, we can switch to another one. The dev and test sets don't need to be large, so this process should not sacrifice much training data. And these details are extremely important when conducting research using machine learning. A lot of papers get rejected for tuning things based on test sets or not giving enough details about how the tuning was done.